Hey guys, we are looking at the topic in measurement and it's called Practicalities of Measurement. So it is a topic from the start of year 11, but it does come up a fair bit. We've got 5 main sections in the topic that I've written out here. We're going to cover these ones in today's video. The biggest part about this topic are your errors, so absolute and percentage errors. Okay, so we're going to focus a fair bit on that. So let's jump straight into it. So scientific notation, remember, it's always in the same form. And it's like a formula, really. You have the first non-zero number, a decimal point, every other number, times 10 to the power of some other number. So for instance, let's have a look at, say they wanted you to put this number into scientific notation. We need the first non-zero number, so 2, then the decimal point, then every other number. Okay, so I filled in the requirements of that part of the formula, times by 10 to the power of something. Now, to work out what it is to the power of, it's just how many jumps you had to do from the original number of the decimal point where it is in your new number. So let's have a look. The original number had the decimal point between the 4 and the 2, so it jumped 1, 2, 3 places to get it to where it is here, which means I just have the power of 3. So let's just look at one more. If I have 0.68431, the first non-zero number, okay, which means I need 6.8431 times by 10 to the power of, how many jumps did I do? Well, from the old number to the original number, I did 1 jump. Okay, so I have power of 1. But note this time, I actually jumped the other way. The first question I was jumping this way, and the second one I was jumping back this way. When you do jump in the opposite direction, we put a negative on the power. Now, I remember being at school and that part would just confuse me. It's like, when are they negative, when are they not? The best way to think of it is the negative numbers, or the negative powers, are when you have 0 point numbers, okay? So anytime there's a 0 point, you're going to jump in the other way, so it's going to be a negative, okay? So one last example, let's think about 0.000643. Okay, I need first non-zero number, the rest of the numbers, times by 10. How many jumps did I do? I went 1, 2, 3, 4, because that's where the new decimal point is there. So it's a power of 4. It's a 0 number, so it's negative. Okay, now don't forget, you can always just put that exact thing in your calculator, press equals, and see if it gave you back the question. It's a great way to check. If I have the number 3.42, all right, we go, all right, well, how many significant figures? There's 1, 2, 3 significant figures. Now, what happens if I put a 0 here? Does that change my measurement at all? No, it doesn't. It's still the measurement of 3.42. So we don't count the zeros if they are in this direction on the ends. Okay, so we don't count the zeros on the ends in that direction. Okay, what happens though if I put a 0 here? Go, well, no, it hasn't really changed my measurement, has it? It's still the measurement 3.42, so would it still have 3 significant figures? This is where it can change. 3.420 means they've rounded to 3 decimal places, or they've measured to 3 decimal places, I should say. But if I didn't have the 0 there, they've only measured to 2 decimal places. So putting that 0 there shows that they've actually measured more precisely. So the rule is, we call them trailing zeros. Okay, so trailing means that they are zeros, how do you spell that? Zeros? Yep, after the decimal point. So they do count, okay? So there's quite a few ins and outs, and that's where significant figures can get confusing. So let's just have a look at if I did 30.42 now. Now there's a 0, and that has definitely impacted my number. That's my measurement has changed significantly by that 0. So we do count that 0, okay? So you have to be careful when you do and don't count the zeros. So that number there would have 4 significant figures. Okay, this number up here has 4 significant figures because we don't count that, but we do count those ones. But then, just to make it a little bit more confusing, what about the number 200? How many significant figures? Well, 2. Oh, sorry, not 2. 1 significant figure. Yeah, I know. So the rule is you count zeros if they are in between. So let's make this a little summary. In between numbers. We also count zeros if they are after a decimal place. So any zero after a decimal place, we do count the zeros, okay? Any other time, we don't count zeros. So these are the 2 times we count zeros, all right? So let's just do a couple of examples together. Let's think about, okay, oh, I'm running out of room. I'll go over here. 60. Okay, it has 1 significant figure, the 6. But if I have 603, the 0 is in between numbers, so it has 3 significant figures. What if I had 6.03? The 0 is trailing a decimal point, so it's after a decimal point. So I do count it, also 3 significant figures. If I had, let's go 6.00. Still zeros after a decimal point, still count them. 0.42, interesting one. The 0 is on the end, okay? We're not counting that. It's before a decimal place. We don't count that 0. So this one only has 2 significant figures, okay? Now, just to do a last minute recap, one thing I have seen, it comes up more in advanced than standard, but it does come up, it's in the syllabus. What if they ask you to do something with both of them combined? So bringing both significant figures and scientific notation into the same question. Let's have a look. They could say round this to, well, let's say put it in scientific notation and round it to 3 significant figures. I have seen this asked in the HSC, and it's not as easy as what you might think. Let's have a look. The first thing you want to do is put it into scientific notation. That's the easy one. We go, okay, 2.30462 times by 10 to the power of 1, 2, 3 jumps, so to the power of 3. Now, this number here, rounded to 3 significant figures. So all I have to do is go, okay, 1, oh, hang on. All right, 1, 2, 3 significant figures. I have to count that 0 there because it's in between the 3 and the 4. It's in between numbers. So my final answer is going to be 2.30 times by 10 to the power of 3. Tricky stuff, but once you really nail both of those in between questions where it brings in both will be easier. All right, let's go to converting units. Now, your converting units, I'm not going to go into a lot of detail. It's about just knowing all the different things you have to convert. So that comes into converting energy. So if you can't quite remember all your energy conversions, so watts to kilo, watts to megawatts, they're pretty straightforward because they're all just 1,000. You just have to know the order, okay? However, one major area of weakness people seem to have is they say, okay, well, I know 1 centimeter equals 10 millimeters, but 1 centimeter squared doesn't equal 10 millimeters squared. And that is what people assume, and it's wrong. Okay, I remember teaching this to you guys, most of you in year 11, and I said there was 2 ways. You could just remember what I'm about to show you, the formula, or you could remember how to work it out. Let's think about this. If I had a 1 centimeter by 1 centimeter by 1 centimeter square, that is the same thing as 10 millimeters by 10 millimeters. So if I found the area of this square in centimeters, I would say that the area equals 1 centimeter squared. But if I found the area of this square in millimeters, then it would be 100 millimeters squared. See the difference? So what does that mean? 1 centimeter squared is equal to 100 millimeters squared. So if you've already worked out the area of something and you get an answer of 4 centimeters squared in your answer, and they said find the area in millimeters, you have two options. You could have converted everything to millimeters originally, then just found your area, which I suggest, or take your answer of your area that was in centimeters squared and use this conversion into millimeters squared. Really important. So then you could do the exact same thing with volume. If I said, okay, well, what about cubed? That was a 1 centimeter cube. Let's think about that. The volume would be still 1 centimeter by 1 centimeter by 1 centimeter, 1 centimeter cubed. But my volume in millimeters is going to be 10 by 10 by 10, which gives me 1,000 millimeters cubed. So 1 centimeter cubed equals 1,000 millimeters cubed. And that's another one. So two things, either remember these conversions, which it's just, I don't suggest because it's piling more things into your mind that you need to remember, and there's quite a few, or remember how to do it with a little square. So then the same thing then applies is imagine if you had a meter by a meter by a meter, okay? That's 100 by centimeters by 100 centimeters, okay? So you would do the exact same thing and find the conversions. There will be a list in your textbook, in the Year 11 textbook, which is on our Class Compass page, and you could probably find the summary. Otherwise, just Google area, volume, unit conversion summary, and there'll be something on there if you just want to print them out and memorize them, okay? All right, this next one, okay. This is what you need to know, that in terms of the nutrition, 1 calorie is 4.184 kilojoules. So if you want to know then what 1 kilojoule is, what you would do is take 1 calorie and divide it by the 4.184. So all that they're going to do is get you to basically use rates, I guess, and say, well, okay, well, what would happen if I had 4 calories? What would happen if I had 80 kilojoules? Okay, so it's going back and forth between those two conversions, all right? And lastly, that energy stuff, it's just those kilowatts, watts conversions, okay, and reading energy charts. So I'm not going to go into that. If you want to download a summary on your energy or look in your book from last year, they'll be in there. The one I really want to focus on is absolute error. So, come on, here. All right, best way to explain it. Let's think about if I said a measurement was 7.5 meters. Let's think about this. And I've just said, oh yeah, the length of my pool at home is 7.5 centimeters. You go, okay, all right. Well, let's think about that. It looks as though you've rounded to 1 decimal place, right? Because it's in terms of 1 dp. And you think, okay, well, it could have been then all the way down to 7.45, and then all the way up to, but not including 7.55, right? So, and even further, let's just say it was even more than that. You could go further down, but the idea is 7.5. We know that that lies in between these two, because if you rounded 7.45 to 1 dp, it would go up to 7.5. And if you rounded 7.5 and anything up to that, not including it, it would also round back to 7.5. So what we call the difference in between here, this is an error in the measurement. So when you ever get given any kind of measurement of the length of my pool is 7.5, there's an error in there where someone's rounded somewhere, okay? So what we have is a few formulas to remember. This is our first one. It says the absolute error is just plus or minus half times by the smallest unit of reading, okay? So let's forget the formula for 1 second. Let's come back up to this 7.5 question. The absolute error is plus or minus a half. Okay, so, sorry, hang on, wait a second. The absolute error in this case is plus or minus a half times by what we call the smallest unit. This measurement of 7.5, we are assuming they're measuring every 0.1 of a meter. Okay, so all we're going to have to do then is multiply them together and it will get your answer here. Which makes sense, right? Because it's 0.05 up from here is the highest value we could have had, and 0.05 down from here is the lowest value we could have had. So that there finds you, and it's plus or minus because you can either add it on, it's either bigger or smaller by 0.05. So I could then say to you, all right, what is my upper limit? All right, and all we have to do is say, well, take the measurement and add the absolute error. Okay, and in this case here, we would say, all right, we could go take my measurement 7.5 and add my 0.05, and I would get 7.55, which is what we said was here. And then the same thing here. If I took my 7.5, if I subtracted off my 0.5, then I get what we also call as the lower limit of reading. So I take the measurement and I subtract the absolute error. That's why the absolute error is given as plus or minus. Now, I probably could have picked a nicer number to start with. If I just said, okay, what about the number 6? Let's say the width of my pool, it's a big pool, is 6 meters. That one, let's think about it logically. We go, okay, well that could have been all the way down to 5.5 because that rounds up to 6, and all the way up to, but not including 6.5. All right, so let's check it over. We know, okay, well the error that it's recording up each end is 0.5 down there, 0.5 up there. If we use our formula of a half times the smallest unit, well this is measured to every 1 meter, let's say. So it's going to be plus or minus a half times by 1, which gives me plus or minus 0.5, which is this guy here. So then I would say, what's your upper limit? Add it on to 6, get 6.5. What's your lower limit? Subtract it from 6, get 5.5. So you might think, well, why do we need these formulas if it's pretty straightforward like that? We could just work that out. It's because you're going to get questions like this. What if I gave you 12.3807 kilometers? Okay. Again, if you're good with your decimals, you could probably work it out, but it's just nice and easy to go, oh yeah, it's half times by, this is measured to every 0.0001 kilometers. Get that, and then add it to it, subtract it to find your upper and lower limits. So the last thing is your percentage error, okay? So the percentage error, if they say calculate the percentage error of the measurement 2.3 kilometers, we go, all right, there's a formula. It's as easy as you take your absolute error, you divide it by the measurement, and then to turn to a percentage, we times it by 100. And that there is your percentage error. Again, you're going to have all this in your Year 11 book, but I'm just trying to revisit it for you. So all you're going to do is say, okay, what's my lowest limit of reading? What is this, the smallest measurement? It's measured every 0.1 kilometer. I need to times that by plus or minus a half. I get plus or minus 0.05. So my absolute error is 0.05. Divide that by my measurement of 2.3 and times it by 100, and that will give you your percentage error. Whew. All right. See how you go with that information? What I would like you to do now is I have posted on our compass this, okay? And it's an entire section of past paper questions all on this topic. Not just that, it then has the work solutions. Okay, so our revision we're going to be doing is I recap a certain area, give you a bunch of past papers on it. Recap an area, bunch of past papers. Okay, so this one is for today. So get that done for me over the weekend if you can.